So today's lesson is exponential functions. We're in 1.6 in your book. But before we jump into the exponential functions, I wanted to go back and review just how to create an XY table. So when you're given a function, like here we have y equals 3x, you can just choose values for x to plug in. You can choose whatever values you want, but generally some negative, some positive, and 0 is good. And if we're going to want to graph it, we don't want to choose really large numbers because that means our graph needs to be really large. So I've just already chosen these numbers for you. So if I plug in these numbers for x, 3 times -1 is 3 times 0, 3 times 1, 3 times 2. And that gives us 4 ordered pairs that we could now graph. And what would it create? What kind of a graph? It looks like this. A line. Okay, this one, however, what's different about number 2? The exponent is a variable. So not just does it have an exponent, but the exponent itself is a variable. So this is not going to create a line. This is going to create an exponential function, which is a curve that looks more like this. So when x is -1, that's 2 to the -1. So you have to bring it down. So 1 over 2 to the first, which is just, okay. And then 2 to the 0, 2 to the first, and 2 to the second. Perfect. So you see that even though the x is increasing by 1 every time, is this increasing by the same amount every time?
No.
No, and that's how we know it's not linear. Linear, they both have to increase at a constant rate. So, yes, I'm just pointing it out for now. Okay, so for this one, we have y equals 2 times 3 to the x. What happens first, the multiplication or the exponent? The exponent. So we're going to do 3 to the -1 first, which is 1/3. And then times 2 would give us 2/3. 3 to the 0 is times 2. 3 to the first times 2, times 2, 6. And then 3 squared is 9 times 2 is 18. So that's just a quick review on plugging numbers in, what they look like. So we're going to look at characteristics of the graph of an exponential function. So here's your core concept. This is on page, what in your journal?
29.
Page 29 in your journal. And we're going to go through and I would have you read it, but since we're recording, I'll go ahead and read it. It says the parent function for exponential growth functions. The function f of x equals b to the x, where b is greater than 1, is the parent function for a family of exponential growth functions with base b. So the base is whatever b is. This graph shows the general shape of an exponential growth function. So you see it gets smaller and smaller over here to the left, and as we move to the right, it gets larger and larger. There's a couple things you want to look at. The x-axis is an asymptote for the graph. So have you heard the term asymptote before? I think you may have touched on it last year, but you didn't spend a lot of time on it. So an asymptote is a line that the graph approaches more and more closely, but it doesn't actually touch it. Okay, so the way I like to think about it is if you have $100 and you give me half of it, and then how much do you have? 50. And then if you give someone else half of what you have left, you now have $25. And if you give someone else half of that, you have $12.50. And if you give someone half of that, and if you walk around and continue to hand out half of what you have, do you ever hit a value of 0 in your pocket? No. Because you're only giving away half of what you have. Now, realistically, is that amount going to get so tiny that you can't actually give money out anymore? Yes. But the idea is if it gets smaller and smaller, it gets really close to being 0. Right, it doesn't actually be true. So this line is getting closer and closer and closer to a y value of 0, but never actually touching it. Okay? Then over here, the graph is going to rise. And it generally rises pretty quickly when we're talking about an exponential function. So it rises as we move from left to right, and it passes through the points. Highlight this. 0, 1, and 1b. We're going to do some graphing of these functions, and it's going to be really helpful to know that those 2 points are always on the graph of this function. They're always on the graph. So if I have f of x equals 2 to the x, what is my base number? 2. So I know it goes to the point 0, 1, but it also goes to the point 1b. So it's going to go through the point 1, 2. Now, if you think about these in terms of the graph of the function itself, what is 2 to the 0 power? 1. What is 2 to the first power? So that's where those are coming from. But it allows us to not have to create a table and plug in those 2 points. It just gives us some information that we always know. Now, the domain for this says it's all real numbers. And we know the domain is the x values, right? So is there anything, any number that it's not okay to plug in as an exponent? We've already been working with negative exponents, they're fine. Fractional exponents, they're fine. We've done regular whole number exponents. Is it okay to have 0 as an exponent? Yes. So any number you want can be plugged in for an exponent. And you'll notice that if we're talking about here for x, and we kind of take that vertical line across, there's always a point on the graph for every x. So domain is going to be all real numbers. The range is when you look at it, let me draw one, like when you look at this, and we're running it across. Up here, does it cross the curve somewhere? Yes. Does it continue to cross the curve as I move down? Okay, when does it stop? At 1 or at 0? Is my graph going to touch at 0? Because we said 0 is an asymptote. So, can my graph be down here? No. So my range is everything greater than 0 because the graph only exists up here. Not when we're talking about these. We're not going to talk about any reflections. But you can see that if the graph was reflected, it would be the exact opposite. Yes, but we're not going to look at any of those today. Yes?
Would a reflection be, like, if it was a reflection, would it be like 2 to the negative x, or would it be like negative 2 to the x?
It would need to be a negative out in front of the function. Yeah, not the variable, not the exponent itself.
Okay.
Yes. Okay, so we've got domain and we've got range. All right. So let's talk about exponential decay. That's the next one on your page. What is the difference? How would you compare this graph to the other graph?
This one is reflection on the y-axis.
So both of those things were really great. One of you said that it's going down. Whoops. Okay. One of you said, yeah, it's going down instead of going up. And the other one said, the other one looks like this, right? So they're a reflection over the y-axis of each other. So that's good to see. So the biggest difference for this one is what the value of b can be. What did we learn about b for exponential growth? What was the restriction on b itself? It had to be greater than 1. What is the b value for this one? Okay, so for a growth function, b has to be something bigger than 1. For a decay function, it needs to be in between 0 and 1. For example, like I was telling you, if you were giving away half of your money and cutting it in half and in half and in half, then b would be 1/2. Because that's what we were doing. We were taking half of it and then half of it again and repeating that process. So we notice here that the x-axis is still an asymptote, isn't it? But it looks like it's approaching it over here as x gets positive instead of on the other one where it was as x got negative. Are these 2 points still on our line? Our curve, I should say? Yeah, 0, 1, and 1b. Did our domain change? Nope, the domain can still be all real numbers. Did the range change? Nope, it's still all the y's that are greater than 0. The main difference is instead of growing really quickly, this is decaying. It's shrinking really quickly. Yes?
Well, the y-intercept will always be at 1.
Well, the y-intercept will always be 1 for a function that looks just like this. But they're not all going to look just like that. And I'm going to introduce them to you a little bit at a time. But for this, yes. Okay, so this first one, y equals 2 to the x. Is that going to be growth or decay?
Yeah.
Growth. Why?
Because it's greater.
What's greater than 1?
It's greater.
The base. So on a test or on an assignment, if I asked you to say why, you would say it's growth because 2 is greater than 1. What about on part B? Is this growth or decay? Decay because 1/2 is not only less than 1, it's also greater than 0. And for this one, 2 is greater than 1. So this was growth and this was decay.
Those two greater than or less than statements
For your explanation. Yes, yes. So then this asks us to graph it. So I'm going to graph this first one, y equals 2 to the x. Let's see. And then we'll come to the ones, there's some in your book for you to practice. Just watch for this one. Y equals 2 to the x. Now, do I have anything below the y-axis? No. So I'm going to draw my x-axis down here. I could draw it on the very bottom if I wanted to. I'm not going to deal a whole lot with negatives, but does my graph go into the negative axis? Yes. So I'm just going to draw it right about here. So that's where you get to choose where they go, and you're going to need to kind of think about what you want to determine it. What 2 points do I know are going to be on this graph? And 1, 2. So 0, 1 is right here, and 1, 2 is right here. If I only plot those 2 points, I have a line instead of a curve. So I need something else. I could make a table, or I can plug in another number here. What if I plugged in a 2 for x? If x is 2, what's 2 squared? 4. So I could plot the point 2, 1, 2, 3, 4. What if it was negative 1? What's 2 to the negative 1? 1/2. So that kind of helps me get a little bit more of the curve effect. But I want you to think about what happens as x gets more and more negative. It gets closer and closer. I'm going to graph this on my calculator. Say that again. So it's not a line, it's a curve, and you're not. It's not going to be perfect. You're getting a good picture. Oh, I changed my scale earlier. Hold on. That's not a good. Do you know that if you have changed your scale on your graph and it's something outlandish, like mine goes to y is 1,000, and I don't want that. If you hit zoom and number 6 is standard, it will always take you back to this window where x goes from -10 to +10, and so does y from -10 to +10. Okay, is it crossing at 0, 1? Are those other points, is 1, 2 on our line, our curve? Okay, but it looks like over here, it's just laying on the x-axis. So one of the things we can do is we can use the table feature to see what's happening. As x gets larger, like when x is 8, y is 256. Do you see how it climbs slowly at first? 1, 2, 4, 8, but then only in a few steps we're already at 128? Okay, now if I go up, I get what happens when my exponent is negative. And what's happening? Right. And, uh-oh, what's this mean?
I mean, it's too big and too small.
Okay, this is important. Write this down in your notebook. When your calculator says E negative 4, it's like scientific notation. So that's like saying, this one right here is like saying 9.8 times 10 to the negative 4th. Which means we've moved this decimal 4 times to the left. So this number is 0.00098. So what that tells us about this is our y values are becoming very, very, very small decimals, right? Now tell me when it hits a negative number. Why not? It's never going to go below 0. And exponents themselves cannot make a number negative. We talked about in the last lesson, if we have 2 to the negative 100th, that really means 1 over 2 to the 100th power. So the denominator is a very, very large positive value. So it's never going to cross that line. Okay, I'm going to go ahead and stop this recording here, and then we'll talk about the next part in the next section.